Okay. So last time we discussed the projective embeddings of projective varieties X into Pn, and then this Pn carries the canonical invertible sheaf O of 1, and we can restrict this invertible sheaf to X. Like this. And last time we discussed sort of ideology that projective embeddings from varieties to projective space are the same as those pullbacks, so invertible sheaves on X, called very ample invertible sheaves, along with a basis of space of section. So the data of F are the same as the data of n+1 sections S1 and sorry S0, so on Sn of well, sorry, global sections on X of this pullback. And these sections should generate the fiber at any point, such that S0 and so on Fn do not vanish simultaneously at any point X. Okay, this was discussed last time, and today I wanna somehow say the same claim in other terms, so a reformulation. So suppose we are given an invertible sheaf, and in case it gives rise to an embedding, recall that it was called very ample invertible sheaf L on X, and a few sections. S0 and so on Sn, spanning a vector space say V in global sections of this line bundle. Then we have an embedding F from X. Well, we have a map actually, but in case of very ample, it is a closed embedding. So in fact, this Pn is the projectivization of the dual space V dual. And how is it constructed? This is very ubiquitous, I would say, a very important construction in algebraic geometry. So I want to stress this construction, and you will go across it many times. So any point X goes to a point in this projectivization of the dual space, and a point in the projectivization of the dual space is a hyperplane in the original space V, right? Hyperplane say H sub X in V, and this is formed by all the sections S in V, such that those sections vanish at this point. Okay, so we know that this is not the whole space, because by our assumption, not all the sections S0 through Sn vanish at X. So there are some sections that do not vanish at X, right? On the other hand, this condition, this vanishing condition is a codimension 1 condition. So then it specifies a hyperplane. This is Hx. Okay. So here is the construction, and once again, L and V is called variable. If the corresponding map F from X to N is an embedding. Okay, so in other words, X identifies with its image inside Pn, and well, L is called variable if there is a subspace of sections well, such that those sections somehow distinguish between all the points. Okay, satisfying the above assumption. Okay, and maybe one easy maybe remark is that if X is affine, so X lies in N, or maybe N small n, then just the trivial line bundle, the structure sheaf, invertible sheaf, is already variable. Okay, and it gives rise. Well, if we take the sections as 0 equals 1, and then S1 and so on, Sn corresponding to the coordinates in An, then the corresponding LV gives rise to the embedding X into An into Pn. Okay, so this was some repetition about ample invertible sheaves, line bundles, and their relation to projective embeddings. Okay, now let me also repeat a few words about the direct and inverse images of general sheaves. Just in case you didn't yet look it up in Kemp generalities. On the push forwards and pullbacks. So we have X mapping into Y, and so I claim that the push forward goes from quasi-coherent sheaves on X into quasi-coherent sheaves on Y, and there is the pullback that goes from quasi-coherent sheaves on Y into quasi-coherent sheaves on X. And let me explain. They are adjoint, form a joint pair of functors, but let me explain why do they take quasi-coherent sheaves to quasi-coherent sheaves. So just from the definitions for construction. The push forward is left exact. The pullback is right exact. And both commute with direct limits or co-limits in modern terminology. Okay, so now let's prove that the pullback takes quasi-coherent to quasi-coherent. So maybe let's call this A, and let's call this B. So let's prove B. So it's a local question. On X and Y. So we might assume both X and Y affine. And so we start with a sheaf on Y, but we know that any quasi-coherent sheaf on an affine algebraic variety is the localization of some module over the ring of global functions. So it's localization of model M over the ring of global regular functions. And we have a morphism, F star, so to say, from global functions on Y to global functions on X. And we want to prove that the pullback of this localized module is just the localization of the extension of scalars, so to say, over k of y with k of x, and this whole this whole thing is localized. Okay. So let's check this. Just choose a presentation. like the ring of global functions to some power. These are relations, these are generators, and this is our module M. Okay, and then we know that the localized sequence is also exact, like the structure sheaf of y to the power I, to the structure sheaf of y to the power j, to this localized module. It's also exact. Okay, and since we know that the pullback is right exact, just because the naive pullback is exact at all, and then tensoring with OX is right exact. Yeah, so it's right exact, and hence we have the similar presentation. OX tensor in the power I goes to OX in the power J, goes to the pullback of M tilde. And this is exact. And now we are done, because it means that the pullback of this localization, that is our prime interest, is the co-kernel of this presentation. And this presentation is exactly the pullback of the presentation downstairs on Y, and that's it. Well, maybe I should say global sections. It's just this, the extension of scalars of our original module. Okay, that's what we wanted to prove. And now let's prove that the push forward is takes the coherent quasi-coherent sheaves to quasi-coherent sheaves. And this statement is local on Y. So again, we can assume that Y is affine.
А локализацию нужно дополнительно ставить m-тензор kx?
Well, I just say that the global sections of this, so for certainly this the pullback of M tilde being this co-kernel is a quasi-coherent sheaf. Okay, now we only want to identify this quasi-coherent sheaf. The quasi-coherent sheaf on an affine variety is identified by its global sections, and the global sections are just like this, the extension of scalars of the original model M. Okay.
Спасибо.
So we can assume that the base is affine and say G a regular function on the base. And then if you remember all the various equivalent definitions of quasi-coherent sheaves, then well, according to one of equivalent definitions of quasi-coherent sheaf, we have to check that the co-limit of 1 over G to some power of the push forward of our sheaf is isomorphic to the direct image of this direct image where J is the open embedding from the base open set in Y into Y. Okay, that's what I have to check. But now, since F was assumed to be quasi-coherent, we can apply the same property upstairs, and so we know that the colimit of 1 over pullback of this function to the power I over F really is the well, maybe J prime, I should say, F, where J prime is the open embedding D, the pullback of G into X. Okay, and now we're done because we know that the push forward commutes with colimits. We can rewrite the desired limit of sheaves like this. J prime push forward of F, and this is equal to J star F star F. Okay, the second equality is just evident. Okay, there we are. Okay, so these were the basics of quasi-coherent sheaves factorialities, and we are done with this. And now let's move to a completely new subject that is long overdue, and I understand there must be a big popular demand for the notion of smoothness. Yeah, we already mentioned these notions many times, and maybe even in a sense used it, and we'll have to use it many more times. So this will be our next big topic. And today we'll only start, and hopefully we'll continue next year. So let's start with tangent and cotangent spaces. So I have a point in a variety, and it will give rise to a tangent space and cotangent space. And certainly you all know those notions from differential geometry, and maybe you remember that in differential geometry you first define a tangent space and then just dualize and get cotangent space. But in algebraic geometry, the cotangent space is more fundamental. You first define cotangent space, and then, in a sense, dualize it and obtain tangent space. So it's easier
Почему
to
оно более
obtain.
фундаментально? Это мы сейчас поймем.
Well, we will just define it right away, and you'll see. It's easier to do somehow. It's easier to define the cotangent space and then from it the tangent space. So by definition, Zariski cotangent space like this is just the quotient of the maximal ideal modulo its square. In the local ring, the maximal ideal. Okay. And well, I may immediately give the second definition. The risky tangent space is just the dual one. Certainly, it's a module over the base field, so you can just a vector space over the base field, so you can dualize it. Finite dimensional vector space over our base field K. Okay.
В квадрате можно поставить.
Yes, here. Yes, thank you very much. Thanks. So now immediately, maybe I should say point C in the same definition, there is a notion of differential. Dx of a local function say f in this local ring, then differential dx f lies in this cotangent space. Just is the image of f minus the constant function f of x. Okay, so this guy lies in the maximal ideal because it vanishes at x, right? So it's the image of this modulo, the square of maximal ideal. Okay, and then it has the following basic properties of the differential. Say first, the differential of the constant function is 0. That's evident. Second is it's linear. It's also evident. Differential at just one point. And the third is also not hard. The differential of the product satisfies the usual Leibniz identity. Okay, that's also easy. And now the next lemma is already very important and substantial. So the first part is that the dimension of this vector space has something to do with the dimension of the initial variety x. Namely, it is at least the dimension of x, and maybe more precisely, the local dimension of x at this point. And the local dimension at this point is the maximum dimension of irreducible components of our variety containing this point. Okay, so certainly this point x could be just an isolated point. That's somewhere far you could have another component of big dimension, but it certainly does not contribute to the dimension of the cotangent space. It's a local notion. Okay, and the second claim is its multiplicativity, so to say. So the cotangent space at the product point of x1 times x2 is the cotangent space of the first factor plus the cotangent space of the second factor. Okay, and the third is that you don't need to localize too much. So if x is affine and we have a maximal ideal corresponding to the closed point x small. Now we already had this notation German M for maximal ideal in the local ring, and Kempf has a very good notion of Nx in K of x, the corresponding maximal ideal. Then you don't need to localize anymore. I mean, the cotangent space is just this maximal ideal modulo its square. Okay, and it will be the same as the maximal ideal in localization modulo its square. Okay, so let's prove this. Okay, so we can for part A, it's local, so we can assume that x is affine and the local dimension equals the global dimension. Okay, so we will remove all the far away components that may change the global dimension. Okay, so let us choose a basis. Of mx modulo max squared and lift it to global functions on x. Well, again, we can perhaps we'll need to shrink our x to make these functions global, but it doesn't matter. So we'll have functions f1 and so on, fm global on x, such that all of them vanish at point x, and their differentials span the cotangent space. Okay, so now we have to check that the number of those differentials is at least dimension of x. And to this end, let's consider the zero set of the ideal generated by those functions, and the corresponding zero set. So let's call it maybe k inside the global functions, and say let y be the zero set of this ideal k. Then at least we know that x is contained in this zero set by definition. And let's say J be the ideal, the maximal ideal of X in, again, the same global ring of functions. Then clearly K lies in J, and by our assumption, or by our choice of those functions, f1 and so on, fm, we have a surjection on the fibers. K x surjects onto Jx, okay, at the level of fibers. But then, if you remember, certainly these are all ideals, or the corresponding sheaves are quasi-coherent sheaves, and they're in fact coherent sheaves. And for coherent sheaves, we had some very, very important property that you can check the surjectivity on fiber, okay? And you do have this surjectivity on fibers, so it means that this inclusion from K to J is in fact an isomorphism in some neighborhood of X, okay? It's an inclusion and it's surjection, so it's an isomorphism in a neighborhood of X. So this embedding is actually an isomorphism.
Когеренты пучков это неверно.
For quasi-coherent sheaves, you don't have such criterion. Yeah, but we discussed it a few times ago. There was some lecture that was dedicated almost uniquely to this discussion, but now we are using the fruits of this discussion. So this is an isomorphism in a neighborhood of X. Okay. So in other words, X is an isolated point of the zero set Y. Okay. Now we had the principal ideal theorem that said that when you cut something by the zero divisor of a function, its dimension drops not more than by 1. Yeah, we also discussed this when we introduced divisors. Yeah, V divisors or Cartier divisors, and there was an example how V divisors can behave badly, but the Cartier divisors, there are zeros of functions locally, they always behave in a good way. So the intersection with the zero divisor of a function drops dimension by 1 at most. I mean, you may have something already inside this divisor, so when intersect with it, nothing will change. But if there is some drop of dimension, it's at most 1. It was called principal divisors theorem, and its corollary a couple of months ago. So it means that in our situation, that since we have just m functions that cut out X, that the dimension of our variety minus the number of these functions is not more than dimension of their set of zeros. There is just 1 point, so has 0 dimension. Okay, so we proved this estimate. And by the way, let's maybe immediately give an example where this inequality is strict.
And isn't it called like principal ideal theorem, not
Oh,
principal?
sorry, principal ideal. Yeah. Thank you very much, Altan. Yeah, I'm sorry. Principal ideal theory. Though somehow morally it's just the same. Okay, so let's consider an example where the variety is one-dimensional, for example, but its cotangent space is, say, two-dimensional or more. So somebody like Anna Maria Rauch, can you give me this example, please? And if not, maybe Sergey Aleshin, can you think of some example like this? So I have a curve, one-dimensional variety, but its cotangent space at a point, at a singular point, will be higher dimensional, like two-dimensional. Can you give an example? I think you already had it in your assignment.
Попробовать
Okay.
какой-нибудь k от xy, фактор по xy.
Absolutely, yeah. So x is just this, I mean, the coordinate cross. The cross in just A2. So in other words, it is the spectrum of k of xy modulo xy is 0. Okay, and the maximal ideal of the origin will be generated by x and y. So what will be? We didn't prove it yet, but we will momentarily. Evident. So instead of the maximal ideal in the local ring, let's consider the maximal ideal in the global ring. So M0 is just xy, and it contains n0 squared. So what is this 0 squared? What are the generators?
X квадрат, xy.
Yeah.
Y квадрат.
Oh, sorry, y squared. Yeah. Okay. So the quotient is what? Just two generators like this. Okay. So two-dimensional. And in fact, another example. So this was irreducible curve, and for irreducible, any suggestions?
Just this curve that passes through 0 two times, like y squared equal to x cubed plus x.
Yeah, the cusp.
Cusp, yes.
Absolutely. Thank you. Maybe my drawing is bad. Let me try once again. Maybe it's better. I mean that the there is one tangent direction, sort of. Okay, and then globally it somehow you give just one irreducible component. Fine. So now let's go on with the proof. And let's. I forgot what we are proving. Part maybe C. Let's prove part C. So about replacing the local maximal ideal. Yes. Pardon me.
B.
Oh, we will prove B. Yeah, we will. But let's first prove C. So I mean, you do the global computation and then localize it, and nothing changes. So the point is that any function in the complement to this maximal ideal of the point acts invertibly in this quotient modulo the square. Just because it has non-zero value at the point x, and that's enough. And hence, when you consider this global definition, nx modulo nx squared, it is the same as if you localize it. Just localization with respect to the multiplicative set S equal to the complement of x without nx. Okay, and then the localization is exact, so you can perform it inside. So you first take nx and then localize it at the maximal ideal, and then take quotient modulo nx squared localized at the maximal ideal. Okay, and now this is already mx modulo mx squared. Okay, so that's easy. And finally, we can prove part B, the multiplicativity. I mean, it's easier in this order because now we can use the global maximal ideals without localization. So the cotangent space at x1, x2 to the product will be equal to the maximal ideal at one point, tensor the functions on the second copy, plus the functions on the first copy, tensor the maximal ideal of the second point, and this whole thing modulo the square of it. Okay, and then you obtain just nx1 modulo nx1 squared tensor k, because that's what remains from the second factor, plus k tensor nx2 modulo nx2 squared, and that's what we want. That's just the cotangent bundle of the first variety, plus the cotangent space of the second variety. There we are. Very good. And now comes the key point.
Почему остается К? Не очень понятно.
Pardon me?
Почему остается К?
Because how to say this? How to say this? Well, because how to say it?
В смысле, что
Ну,
если у нас есть какая-то функция,
Yeah.
ну там, скажем, в k от x1 мы можем вычесть константу из нее так, чтобы она занулялась какой-то в нашей точке.
Yes.
Да, и, значит, всякое реорганизовать это.
Yeah, for example, yeah, but well, how to say it? I'm sorry.
Maybe you can say that nx1 tensor k by 2 this ideal squared is equal to nx1 squared tensor k of x 2 without square, because
Well,
because when you take square of polynomials you get
well, it's not quite true that in any function on x2 admits a square root. Yeah, that's not what I want to say.
Maybe it's because nx1 tensor nx2 lies in the square. Is it true?
No, that's not true either.
But any function could be represented as 1 times this function.
Yes.
Maybe that allows us to say that the square of this ideal is itself.
That I believe is true. Yes. Okay, and also in the square we'll have crisscross terms. Yeah, like kx2 tensor kx1. So I think, well, I think it's really evident. Only it's my psychological problem. Okay.
Извините, а как в итоге-то разрешился этот вопрос? Я не совсем понял.
The solution is evident.
А как это понять?
Well, if you think of it just 1 minute, you will see that it's evident. So the most important definition for today is that a point is smooth if the dimension of cotangent space at this point is equal to the dimension of x at this point. We know there is an inequality in one direction, but if it becomes equality, then the point is. And in fact, you see that the counterexamples we had at the previous page, they all used clearly singular points. Okay, so the first thing we are going to prove about this notion is that the smooth points are abundant. So if x is an irreducible variety, then it's smooth. How does it? Maybe sorry. It contains an open, non-empty subset U and X consisting of smooth points. Okay. In fact, it's true that the property of smoothness is an open property, so the set of all smooth points is open, but we don't yet prove it. We're proving somewhat less strong statement, and here is the proof. So again, we can assume that the question is local, so we can assume that X is affine. And we will view it inside some affine embedding like this. And so we might also assume that X is it's already irreducible, so it's of some particular dimension, and let's assume that it has codimension D. So n minus dimension of X is D, and we'll prove our statement by induction in D, in this codimension. So first of all, if D is 0, the base of induction, then X is just the affine space, and then it's clearly smooth. Any point is smooth. Yeah, for evident reasons again. Fine. So now if codimension is positive, then there is a function, non-constant function, G, a polynomial in n variables, such that G identically vanishes on X. And now we'll use an evident lemma that if we take, G of minimal degree, I mean, among the functions vanishing on X, in the ideal of X, Jx, then there is some partial derivative, I, such the partial derivative dg over dxi does not lie in this ideal, does not vanish identically on X. And let's prove this lemma. And in this proof, somehow, maybe for the first time in this course, there is a distinction between positive and zero characteristic. So if the characteristic of K is 0, then you see the degree of the partial derivative is less than the degree of our function. So by assumption, our function was had the minimal possible degree in this ideal. So if all these functions, if all these partial derivatives vanish on X, they must vanish identically. So if dg over dxi is 0, then dg over dxi is identically 0, and hence g is constant. And we assumed it was not the case, so it's a contradiction. But now, if the characteristic of k is not 0, is some prime p, then again we obtain that the partial derivatives vanish, but then it does not imply that g is a constant. It only implies that g is some function in pth powers. I don't know how to write it. Maybe capital I, x, capital I, something like this. But this capital I must be divisible by p. So maybe let me write it times p. Okay, so this is some multi-degree, but I mean that all the terms of this multi-degree must be divisible by p. And hence, hence you can extract pth root of this guy. Well, there is pth root of g, namely the sum of pth roots of the coefficients times just pth roots of these powers that are also extractable. So again, this is a regular function. And it vanishes on x. And having a degree less than degree of j, degree of g. That is again a contradiction. Okay, so we proved the lemma. And we can continue assuming the lemma. So we assume that dg over dxn is not identically 0 on x, and by the M-Minotaur lemma, we can change the coordinates. And assume that G is a monic in this last coordinate, xn, and still the partial derivative does not vanish identically. Okay, and now let's consider the following projection. So I have an embedding of x into this divisor, g equals 0 in and now let's project along the last coordinate onto a n minus 1, and x will project there. Let's call this projection, say pi. Then we know that pi is finite. And hence the image of x is closed of the same dimension. Is closed in the smaller space of the same dimension. As x, I mean, and hence of codimension there is one smaller, so d minus 1. We had codimension d, and now the codimension of y in a n minus 1 dropped by 1. Okay, so by the induction assumption, we already know what we want for y. There is an open and non-empty subspace, subvariety in Y consisting of smooth points. Okay, and let's choose. Oops, sorry. Okay. So we choose a point x lying over a smooth point of y. Phi of x is smooth in y, and also this non-vanishing of the partial derivative holds true. So d g over dx n is not 0 at this small x, because there are two open conditions. Yeah, the intersection of two open subsets of irreducible variety x is non-empty, and we can find a point there. Okay, so now we have this cotangent space at the image to y. We also have the differential of the last coordinate, k times the differential of the last coordinate, and those two project, well, map into the cotangent space to our variety x at the point x, but by the construction, this factors through the quotient modulo the differential of function g at x. Or maybe I should say dx. Okay, and what do we know? We know that this differential of function g does not vanish. So maybe I should also say k times this. So this quotient does really well, is really quotienting out something. Okay, so the dimension drops by 1 here. So we will know that the dimension of cotangent space to x is at most dimension to the cotangent space at y. Okay, and for this we already know that it equals the dimension of y, and we again remember that this is the same as dimension of x. Okay, so we did find a point, a smooth point. X is smooth, and x was in fact arbitrary in the intersection of two non-empty open subsets in X. So we did produce some open subset in X consisting entirely of smooth points. Okay, so generically, every variety is smooth. Okay, that's what should be expected. And I still have maybe 10 minutes. Let's formulate some new notion. Then this new notion will be of the Zariski tangent cone. So this will be something inside the Zariski tangent space. And the Zariski tangent space, as you see, might have a big dimension. Yeah, it is dual of the cotangent space, so it has the same dimension as the cotangent space. And if your point is singular, not smooth, then it's bigger than the dimension of the ambient variety, capital X. But this Zariski tangent cone will have the same dimension as the ambient variety. So for example, in case when X was the coordinate cross, xy equals 0 in A2, then this tangent cone will be just the same. Well, somehow X is already conical. The equation cutting out X is homogeneous. So it coincides with its own tangent cone. Nothing interesting. And if X is this cuspidal curve, X squared equals Y cubed, again in the plane, then the tangent cone, or maybe I should say to X, sorry, will be equal to what? How do you think? Any suggestions? Say, Vanya Украинцев. How do you think, what will be this tangent cone?
Да, извини, а ты можешь еще раз повторить, что это такое? Я не понял просто.
I didn't give a definition yet, but I hope it's clear what we're aiming at. So how do you think in this example, this not yet defined tangent cone will be equal to what?
Мошка в квадрате?
Say it again, once again. Do you think that's the whole plane? That's what you say?
Mm-hmm.
No. It will be of the same dimension. You see, so it will be just given by. It will be just the vertical line. X equals 0. So in general, somehow, if you have some equations, if they are all homogeneous already, so it's a local notion. Embed your X into an affine space, and let's say your point is the origin. Okay, then X is cut out by some equations. If they're homogeneous, then they are already. Then X itself is some cone, and it is just the tangent cone itself. Nothing has to be done. Now, if it's not homogeneous, then you just take the smallest degree part of all the equations and forget everything else. Like here, you had x squared equals y cubed. So you forget y cubed because it has degree bigger than 2. Yeah, you're left with x squared equals 0. But x squared equals 0 gives you not reduced variety. So you take this ideal, you take its radical, and there you are, something like this. Okay, so the general definition is as follows. You take the so to say associated grade. So you take G sub x is the direct sum. You start with K, then you take the cotangent space. mx over mx squared, and then you take the next term, mx squared over mx cubed, and plus so on, the infinite sum like this. But it's a graded ring. And you can take its spectrum, and that's it. So well, let me go to the next page. Cx, by definition, is the spectrum of sorry, maybe no. Let me erase everything. It's a graded ring, but unfortunately, as we have just seen, it can have nilpotence. So sometimes with nilpotence. So we take its quotient modulo nilpotent radical, say gx modulo n, and then take its spectrum.
Is the nilpotent radical always homogeneous?
No. Why? You ask why the result is the cone. Yes, certainly. Yes. Maybe let me say it in some other words. We can consider this Zariski cotangent space. It's a vector space, and we can take its symmetric algebra. Okay, and now there is an evident morphism from this, in fact, surjective morphism from this surjective algebra, from this symmetric algebra onto Gx. Okay, so because this is the direct sum over all positive n of mx over mx squared to the symmetric power n, like this, and this is the direct sum over all positive n of mx to the power n to mx to the power n plus 1. Okay, and clearly there is just a term-wise map like this, and it's clearly surjective. Okay, so maybe let's define J as the kernel of this map. Let's call it P, and J inside the symmetric algebra is the kernel ideal. And now, by definition, the tangent cone is defined by the homogeneous ideal the radical of J. Okay, so unfortunately the time is over, and I don't have time to explain the geometric meaning of this ideal. This will be the first thing we do next year. And I hope we'll meet next year, maybe on January 16th. And it'll be twice a week, Tuesdays and Thursdays at the same time, 2:30 or 2:40. And well, so I hope we will move twice as fast now from now on, and we'll be able to do something interesting in the next semester. But anyway, accept my congratulations with the end of this semester, and I hope you will have good grades, and congratulations with the next new year. Good luck with your exams and next year. Thank you. So if there are any questions, let's discuss them. Or else I am
В следующем
stopping.
году будет полный семестр или один модуль?
Oh, yes. It will go from January to June for the whole semester, twice a week. So it'll be a thick course from now on.
Какая будет основные темы, какая цель будет следующего полугодия?
So the main goal will be to finish this book by George Kempf. And when we finish this book, we'll have some more advanced topics. Well, the possibilities are Hilbert schemes, some more advanced theory of curves, or maybe some Frobenius splitting in fine characteristic and its applications. Well, hopefully we'll have time to cover some parts of all those.
And do you plan to discuss schemes and the related?
Oh, yes, absolutely. Yes, yeah, Altan is right as always. First thing after we finish with Kempf, we'll discuss schemes. Yeah, absolutely.
Хотя сколько
But
курс
somehow,
будет весить?
pardon me?
Сколько будет курс весить? 6 кредитов?
I think so. Yeah, as a thick course. Yeah. Yeah. So if you remember what was with invariant theory, if it was 6 credits, then the same will be here. Yeah. But one nice point about this book by Kempf is that although it does not introduce the notion of schemes, it does everything. So you just introduce this notion, and then everything goes word for word. So you don't really need to do anything new. You just introduce this notion, and everything is already done.
But the generic points and
Oh, yes, you do have, yes. There is some great language by Grothendieck, but all the theorems in Kempf, they carry over to schemes just literally. You don't need to do any extra work.
Okay, thank you then.
Thank you. So hope to see you next year. Have a good year. Okay, so I'm saving this. I'm stopping the recording.